Hi, this is Dr. Goldstein, and I am going to discuss the chain rule. So, some nice intuitive motivation to get us started. Let's say that a shoe company is analyzing their profits, and they know that they make a $14 profit per shoe, and they make 300 shoes per day. And they want to answer the question of how much profit do they make per day. So, this is not hard to answer. We look at this and we say, okay, this means they make a total of 14 times 300 in profits per day. Okay, so what on earth does this have to do with calculus? So we realize that this whole problem is a statement about derivatives. This is a statement about derivatives because derivatives are a rate of change. And so if P represents our profit and S represents the number of shoes, then what we're saying when they make a $14 profit per shoe is we're saying that dP ds is equal to 14. And if we let T be time, measured in days, when we say that they make 300 shoes per day, what we're saying is that ds dt is 300. So what we're calculating when we multiply 14 times 30, this profits per day, is dP dt. So this is the amount that our profits change over time, and we're multiplying the amount that our profits change according to how many shoes we make. We're taking that rate and we're multiplying it by this other rate, how many shoes we make per day. And so this is what tells us to take 14 and multiply it by 300, and we get 4,200. And one nice thing that you can notice here is that our units are consistent across this entire problem. So the units of 1,400 is in dollars per day. And if we look at dPds, that is dollars per shoe, and ds dt is shoe per day. So it looks as if our units all sort out across this whole equation. So this actually is the chain rule down here. dP dt is dP ds times ds dt. So let's see, again, what exactly does this look like when we talk about it in terms of calculus, meaning when we talk about it in terms of functions. So note that profit is a function of the number of shoes that are made. So we can write, for example, P of S. So P, profit, is a function of shoes. And what if our function looks like 14S minus 1,700? We have some sort of overhead, $1,700, but we make $14 per shoe, and then our actual profit, we have to subtract that. Okay. Also, the number of shoes is a function of time. So maybe, okay, S of T is given by 300T. So for each day, I make 300 shoes. So what we can notice here is that profit is also a function of time, and we realize this because we take our function P and we stick in S, but instead of just sticking in S, we stick in S in terms of T, and so we get that P is 14 times 300T times that S, minus 1700. And so when we look at p as a function of t, we get that p is given by, when we simplify this, 4200t minus 17. And so remember that we saw that the chain rule said that dp dt is, and again I'm going to color code this, dp ds times ds dt. And you can look at this function p and you can see that dp ds is indeed 14. That's just a linear function, so its derivative is that 14. And that ds dt is 300. And so the rule that we saw before, the chain rule, says that we get 14 times 300, which gives us 4200, which is indeed the slope of this function p of t that we saw. So again, really what I'm pointing out is just how our intuition behind this makes sense when we start using actual functions. When we start using actual functions, we see that, yeah, we can still just multiply dp ds and ds dt. So these are relatively simple functions. What happens? What if p and s are more complicated? What does it look like then? So what if p and s are more complicated functions? Can we still just multiply? Okay, so suppose that p of s is actually 7s squared minus 1700. So ignore the original derivatives that we were working with. Now we have these functions, p of s, 7s squared minus 1700, and s of t, 100 times t cubed. And these are our functions that give us our profit in terms of the number of shoes and the number of shoes in terms of time. So then what we have is that dp ds is 14s when you take the derivative of 7s squared minus 1700, and ds dt is 300 t squared when you take the derivative of s of t. And so if we want to just use our previous chain rule, our previous formula, and to calculate dp dt, so again, you can take s and stick it inside of p, and that gives you dp dt. And what we should get is dp ds times ds dt. We should get 14s times 300t squared. Well, but that's not very satisfying because dp dt isn't a function with an s in it, so we really want to replace that s. Well, but s is 100 t cubed, right? This was this up here. S was 100 t cubed. And so we can substitute that in. And so what we see when we simplify this is we end up getting 420,000. Lost track of my zeros. And then t to the fifth. Okay, and we look at that and we say, yeah, sure. Does that seem right? It certainly doesn't match up with the numbers that we saw before, but again, we changed our functions p and s, so that's kind of to be expected. So does that seem right? Well, if we actually write down what p of t is, so p of t, you get that from taking p of s of t and simplifying it. So we take that and we simplify, And so we have 7 times 100t cubed, that gets squared, minus 1700. And if you simplify that, you end up getting 70,000 t to the 6 minus 1700. And so when you take this derivative, when you simplify this and you just have your p's and your t's, we see, yeah, okay, p prime of t, that's dp dt. That really is, so that's going to be 70,000 times 6t to the 5th. Yeah, that's going to give me 420,000 t to the 5th. Yep, that checks out. So what it looks like is our chain rule here. Again, this is the chain rule. For these particular functions, that's what the chain rule looks like. Our chain rule really seems to hold up in this situation. If we really put this in the context of profits in terms of shoes and shoes in terms of time. So let's abstract a little bit further so that we could really see ourselves using this chain rule in any sort of situation. So what we've said using Leibniz notation is that the chain rule is dp dt is dp ds times ds dt, where we're dealing with this function p of s of t. And the thing that we notice here is that this is a composition of functions. And so that's what the chain rule is telling us, is how do I take the derivative when I have a composition of functions? So the way that we write the chain rule in prime notation, and this may be what you've seen before, it's something that people tend to be more familiar with, when I take the derivative of f of g of x, so the composition f of g of x, I take the derivative of the outside function f, I stick in that g of x, and then I multiply by the derivative of g. So that is what the chain rule is. And to see how this lines up with our Leibniz notation, let's start translating between the two notations. The easiest part is this g prime of x. That is dg dx. Now, the total thing that we're trying to compute over here, we want the derivative of this function f of g of x. Well, this is a function in terms of x, so it's, in Leibniz notation, it is df dx. We want this outside function f not viewed in terms of what's going on in the inside, just viewed in terms of x. And so that's the tricky part of this, of going between Leibniz notation and prime notation, is this middle term here. Here what we're doing is we're taking the derivative of f, but we're viewing it as a function of g when we do that. So we view f as a function of g when we use the chain rule. And so what we end up doing is we take that, the derivative of that, and then we plug g into the inside of that. So g goes inside f prime. And so that is the intuition for going between this prime notation for the chain rule and the Leibniz notation for the chain rule. So again, both of these things are the chain rule. This is the chain rule, and this is also the chain rule. And they look very, very different in these different notations. One of them is usually easier for some people. You might say, I really like one of them, I really don't like the other one. It's sometimes different for different people. All right, so let's look at one more example. I want to look at using this prime notation to take the derivative. So here is a function h of x, and it's just given as the cube of 2x to the 4th plus 1. So again, if I'm going to use the chain rule, I have to remember that the chain rule applies to composition. so I have to look at my function h as one function inside of another function. And I have to recognize that structure before I can apply the chain rule. So I look at this, and for me personally, it's easier to look at the inside function. Here, my inside function is this 2x to the 4 plus 1, and so that is my g of x. And if I want to take the derivative of that, g prime of x, that is going to be 8x cubed. Plus 0, but we won't write that down. Okay, so the outside function, my outside function here is this cubing. So it's x cubed. That's my f of x. And so f prime of x is 3x squared. And so now when I apply the chain rule, my derivative h prime of x, again, I'll write down the chain rule so we know what's happening. It's f prime with g stuck inside, and then you multiply by g prime of x. So I have the derivative of f, which is this 3 blah squared. I stick g of x inside that. Oops, that's not g of x. G of x is 2x to the 4th plus 1. That was g prime of x that I wrote a second ago. That goes on the outside. So here I'll color code this a little bit. Here's my g of x in green, goes there. That's my g of x. My f prime of x is here. That's there, and that's that 3x squared. And then my g prime of x is this 8x cubed, and that goes right here. Okay, so one thing to notice that's going on is that when I write this down, it might make, if that doesn't make any sense to you, it might make more sense to remember that really what's going on is we have f of g, that function g that's up there. We have f of g, and f of g is g cubed, and so f prime of g is 3g squared. And so that's why this translates down here into having to take this 2x to the 4 plus 1 and stick that into the 3 times blah squared. Okay, so again, we can look at the end of this and ask ourselves, okay, but does this make sense? If I actually go and simplify this algebraically, so I square everything out and I multiply by 3 and I multiply by 8x cubed, what you get when you simplify this fully is you end up getting 96x to the 11th plus 96x to the 7th plus 24x cubed. And I'm not gonna do all that algebra out for you. If you really want to, you can do that. And so what happens is if I take my original function h of x from the top, so if I take this all the way down from here and I look at it from a totally new perspective and I say, well, what if I just want to multiply that out instead of using the chain rule? So I have 2x to the 4th plus 1 cubed. And again, this is just some gross algebra that you probably don't want to do. If I multiply that whole thing out, I end up getting 8x to the 12th plus 12x to the 8th plus 6x to the 4th plus 1. And now that polynomial, you can just use your more basic derivative rules to calculate that h prime of x is going to be, so that's going to be 8 times 12, x to the 11th, plus 12 times 8, x to the 7th, plus 6 times 4x cubed. I'll write down the plus 0. When I simplify this, I end up getting 96x to the 11th, plus 96x to the 7th, plus 24x cubed, which is exactly what I got before. This is exactly the same. So this, I mean, if you're skeptical about the chain rule still, this is too much to be a coincidence. So yeah. Again, the chain rule, I'll go back to the previous slide. There's two different forms for the chain rule. You have the Leibniz notation that looks like this, and we have the prime notation that looks like this.